Okay, so let's continue our discussion of this quantity we call the chemical potential energy. So recall that we're trying to find a quantity that would help us predict if a chemical reaction will be spontaneous or not. And we're trying to see if we can find something similar to the gravitational potential energy, which is a quantity we can use to predict if a mechanical process is going to be spontaneous. And so when we look back at that various thermodynamic quantities that were discussed in Chem 11, the only thing that is an energy quantity is the delta H or delta E, right? So that's a measure of the energy that is released or absorbed during chemical reaction. So the question becomes, is this the number that we can use to make prediction of spontaneity of chemical reaction? First off, we know that when delta H is less than 0, the product is going to be more stable than the reactant as illustrated by this energy diagram. The question then becomes, is it true that all exothermic reactions are spontaneous? And on the opposite side, is it true that all endothermic reactions are non-spontaneous? Well, I'm going to show you a number of exothermic and endothermic reactions, but let me just cut to the chase here and say that it turns out that delta H doesn't correlate with spontaneity. We're able to find a number of exothermic reactions that are not spontaneous, and we're also able to find a number of endothermic reactions that are spontaneous. So here are some examples of them. These are all exothermic reactions, and as you can see, they are all non-spontaneous at some kind of condition. So for example, this one right here is just condensation of water going from gas to liquid, a negative 44 kilojoules delta H, which means it's exothermic, but it's not spontaneous. As you know, steam doesn't condense to liquid water at temperatures above 100 degrees. So clearly there's a condition where this reaction is not spontaneous. This is another reaction where it's just liquid water freezing to become ice. We see that the delta H is negative 6 kilojoules, but we know that that reaction is not spontaneous when the temperature is above 0 degrees Celsius. So clearly we can find examples of exothermic reactions that are not spontaneous. We can also see that some endothermic reactions are spontaneous. So if we just flip those two reactions that we just talked about, the liquid to gas now is going to have a delta H of 44 kilojoules, but we know that the evaporation of liquid water to become gas is spontaneous as long as the temperature is above 100 degrees. And similarly, the melting of ice to become liquid water, even though it's endothermic, it is spontaneous above 0 degrees Celsius. We have a couple other examples here of things that are spontaneous. So this one right here is just the dissolution of the salt, rubidium chloride. So if you take rubidium chloride and put it in water, it will spontaneously dissolve, and then the salt will dissociate into ions, even though the delta H is a positive value. What we just learned is that delta H doesn't predict spontaneity. Now, although I'm showing examples of reactions that go against the prediction of delta H, right? In other words, that I'm finding reactions where it's exothermic, but yet it's non-spontaneous. What is actually true is if you look at all the reactions that are possible, most exothermic reactions are actually spontaneous, and vice versa, most endothermic reactions are not spontaneous. So I'm finding you exceptions to the rule, which tells us that delta H is not the main factor that determines spontaneity. However, it does play a role because, as I just told you, most exothermic reactions are indeed spontaneous and most endothermic reactions are not. So we need to look for another quantity, another energy quantity that will correlate always with spontaneity. Now, the way we can find this, at least the way we can find a clue about this energy quantity, is by looking at these exceptions, these reactions that I'm showing you right here. Why is that? Well, because we know that in theory, exothermic reactions are reactions where the products are more stable than the reactant. So we do expect that this reaction should want to happen, right? Because you're forming something that's more stable. The fact that they don't happen spontaneously is curious, and we should see what it is about these reactions that make them not happen spontaneously. Similarly, if we look at our endothermic reactions, we know that these are reactions where the products are less stable than the reactant, right? So the profile of endothermic reactions look like this. So why does it still happen spontaneous in all of these instances? Okay, so we want to look at those specific reactions and see if there's some kind of pattern that would help us predict spontaneity. Now, looking a little bit more carefully at the exothermic reaction, we notice that these reactions happen to have a pattern where you're going from something that is less restricted, so something like in a gas phase here, going into something in the liquid state, which is a little bit more restricted, right? So gas phase particles are really far apart. Liquid particles are still far, but close enough that they could make some kind of intermolecular interaction. Here's another example of a non-spontaneous reaction, you have a liquid going to solid. So that's even more organized, right, than a liquid. So it seems to me that if you're going from something that's really sort of free to move around to something that's less free to move around, a little bit more restricted, a little bit more organized, that process is not spontaneous, okay? So going from here to here is not spontaneous. What about that middle reaction that I didn't talk much about? That one is kind of interesting because you have, if you look at the pattern there, they're all gases. So it's not like one side is gas, the other side is liquid, like the other two example. However, what we notice here is that we seem to have more particles on the left side and we have fewer particles on the right side. And if you look at many more of these examples, you see that that pattern holds. In other words, it seems to be like if you have more particles going to fewer particles, that also causes things to be not spontaneous. Okay, now let's take a look at the other side, which is the endothermic side. And again, pattern we want to look for here is something that will help explain why these reactions that are in theory supposed to be non-spontaneous actually end up being spontaneous. Well, two of the examples we already saw, which is the liquid to gas and the solid to liquid. So now it's sort of the opposite pattern. You're going for something that's more organized, something that is less organized, and with gases is even really no interaction at all, right? So it seems like if you're going from more organized to less organized, this process is spontaneous, okay? The one with the dissolution of the rubidium chloride actually sort of fits that pattern as well, because it's going from solid, which is just particles that are packed together like this, to aqueous solution where the ions are kind of separated, but then they're surrounded by some water particle, okay? So in that sense, you can see that we also are going from something that's highly organized to something that is less organized, and that seems to be spontaneous, okay? Now, the one that I haven't talked about is this one right here. And here you see that we actually have aqueous and liquid. Aqueous and liquid are not that different from each other because remember that aqueous solutions are basically something that's dissolved in water, which is a liquid. So most of in terms of the state of matter is fairly similar. However, what you notice here is on the left side, you have fewer particles. There's a total of 3. On the right side, you have a total of 12 particles. So again, that's sort of like the opposite pattern that we saw earlier with the exothermic, where we got more particles going to fewer. Now we got fewer particles going to more, and that seems to make the process spontaneous. So generally speaking, then, what we can conclude, at least at this very sort of superficial level, is that spontaneous reaction seems to be going from more restricted state to less restricted states. Okay, so for example, liquid to gas, solid to liquid, or fewer particle, more particle. Vice versa, non-spontaneous reaction would be the opposite. It will be going from things that are less restricted, okay, more free to move around, to more restricted. So solid are more restricted, gases are less. More particles to fewer particles also seem to have this problem. So another way to look at it is this. If I give you these two possibilities, right? So let's say I have a perfume bottle right here, and I spray some perfume, okay? So some gas particles. What do you expect to happen? Well, the gases will immediately spread around in that box or room, right? So at some point, the gas particles will be everywhere in the room. I mean, even if you're standing on this side of the room, you can smell the perfume because it's traveled, the gas particles have traveled. And this is something we know from experience. If we do the experiment, we'll find that that's the case. It's very unlikely, in fact, never really happened, that if we spray that perfume at one side of the room, that all that particle of gas will just stay there in that side of the room and never moves, right? We don't see that happen. So again, the idea here that between these two pictures that this is something that is more organized, and this is something that is less organized. So just to summarize that information that we just talked about, it seems like the same pattern that we saw earlier, which is that the systems seem to like to go to a less organized state, right? The more organized state is not something that we see in everyday life. So again, with that perfume example, the perfume will not stay at one location in the room. It will spread, it will travel, the gas particles will travel. Another example is shown right here. Imagine that I'm standing on a truck that's filled with a bunch of brick, and I start throwing the brick on the floor, okay, to move them. What is the likelihood that you will, just by randomly throwing the bricks, will see that structure versus the structure on the right? We all know that by experience, again, what would end up seeing is something that looks like this. The brick will just be all over the place, right? It's not very likely that you'll get a structure that looks like this where the brick is nicely organized. In order for me to do this, I need to put special attention to make sure that that happens. I need to actually stack the brick, and that means I need to put in some energy to actually put the brick in a specific order. So if I just do this process randomly, this is what I'm going to see. Now, in nature, processes happen randomly. There's no specific force that's making something happen, right? And so what we say here again, based on this second example, is that processes tend to
spontaneously end up
in a state where there is more disorder or less
organized.
Either one of these words is fine to use to explain that state. The state where there's more order, it's more organized, is not going to be something that we would see unless we put a special effort to make that happen. Okay. Now, I'll just say here this term order and disorder is something that we often use to explain this idea of the different state. They're not necessarily correct, but it is a helpful analogy to help us visualize what's going on, like how the particles are behaving. And in the next section, we're going to talk about what exactly these order and disorder term mean with respect to molecules.